So I hope you're comfortable with 3.1 to 3.3. Sorry, videos 1 through 3 here, because this next video is not much new. It just adds tedium. And tedium always adds many, many places where you can mess up. So this video is just evaluating definite integrals. And remember, the fundamental theorem of calculus says that if we're, sorry, I always get my big F's and little f's confused. If we have the definite integral of some function, that's just the antiderivative at one and the antiderivative at the other, and you just subtract them. The definite integral of a rate of change is the total change. So the hard part is just finding this antiderivative. What is the antiderivative? And we've done that this whole section. We've been finding tons of antiderivatives. But then we're going to have to plug in and simplify numbers at the end. There's actually two ways of evaluating these definite integrals. So there's the first option, which is straightforward. It's just find the antiderivative the same way we've always found antiderivatives, and then plug in and subtract just like so. And I'll show you that way. But my preferred way, what I'll be doing in most of my examples, is just to convert everything, including the limits of integration, into u. So let's see what that looks like here with a simple u substitution problem. So over here, again, we have an inside function. Again, it looks like something with maybe the chain rule. We don't really have anything else on the outside, so this looks a little weird. But notice that what the derivative of u is. It's just 3. So we don't actually need any x's on the outside because the derivative of u doesn't have any x's either. So I'm going to first show you option 1. What does that look like? So both options will have u be equal to that. So u is 3x minus 1. So du is the derivative of u times dx. So we have the integral, and we're going to have u's and x's floating around. So I'm going to be very clear that x is 0 up to 1. This is just notation saying, what is x actually? Or what are our limits referring to? Because we have two variables. Which one's which? And then we have u to the 4th times dx. Oh, and dx can become du if it had a 3. So let's give it a 3. We multiply by 3, we need to divide by 3. And now this right here is just du. So in option 2, we'd be in a very similar spot, but we would also convert these to u's. All right, now we take the antiderivative, add an exponent, divide by that exponent. And again, we're evaluating between x equals 0 and 1. So we can't plug in 0 and 1 because x should be 0, not u. So we need to put everything back in terms of x's if we're doing option 1. And that's why I don't like option 1. I don't want to put things back into x's if I don't have to. And again, as a reminder, we do not need the plus c because we're using the fundamental theorem of calculus. If this has a plus c and this has a plus c, they cancel. So we usually just ignore the c. So put everything back. U was 3x minus 1. We're still evaluating from 0 to 1. And now I don't need to tell us that x is 0. I don't need to tell you what variable this is now, because now there's no u's anymore. There's just one variable. So it's clear from context. Plug in 1. Oh gosh, I hate this method. I was trying so hard to show you the two options and let you choose, but I'm showing a lot of bias here. We get 3 times 1 minus 5, minus 1 to the 5th power divided by 5. We plug in 1, and we plug in 0. And we simplify. This is 3 minus 1 is 2. 2 to the 5th is 32. This is -1. -1 to the 5th is -1. So this becomes a +5. And we get 33 over 5. I went through this pretty quickly. I'd normally check my answer, but we're going to check our answer with option 2. So option 2 is very similar. Oops. Option 2 is very similar. The difference is that when we get here, the integral of u to the 4th du, we still do the same substitution. The difference is that we also convert these things into u, right? U is 3x minus 1. So if x equals 0, what is u? Because the bottom limit is x equals 0. So if x is 0, u is 3 times 0 minus 1. U is -1. So we're also converting our limits to u's. And again, I don't have to specify that this is u, because everything is u now. We're converting everything to the same variable, but you could if you wanted to. And similarly, we look at our upper limit. If x is equal to 1, what is that in terms of u? Well, 3 times 1 minus 1 is 2. So now we're just integrating this from -1 to 2, and we never have to go back to our x, which for a lot of us is a good thing. So here we go. Ha ha ha, funny joke. Antiderivative, just like normal, evaluating from -1 to 2, and we don't have to go back to this messy thing. All right, so we plug in 2, we get 2 to the 5th over 5. We plug in -1, we get this over 5. That's 32 over 5 plus 1 over 5, because a negative times a negative. And we get 33 over 5, which is great. That's exactly the answer we expected. So again, option 1 is kind of straightforward. You just take the antiderivative normally, get this antiderivative, evaluate from 0 to 1. But if we just convert our limits of integration into u's as well, it's a little cleaner in the plugging in stage. And the plugging in stage is where I always make mistakes. Let's do one more practice. Okay, so there's 2 natural choices of u here. You could let u be the denominator, like we've done before. Denominator is often a good choice of u. Or you could let u be natural log of x, because that's kind of an inside function. Which one do you think is going to work? We like inside functions, and we also want to make sure that our derivative is sitting around somewhere. Well, if u is this, the derivative is 1, so yeah, that kind of works. And actually, yeah, if this is it, the derivative of natural log is 1 over x, and we do have a 1 over x, right? An x in the denominator. As a side comment, this will never work, because this isn't a substitution at all, right? If u is x, all that is just changing your variable, but you're going to get the exact same functions. So u is x, that will never work for any integral, unless you just didn't need substitution to begin with. So we don't want this. This is the u sub that we want. So du will be the derivative of u with respect to x times dx. Now let's be a little bit more careful with our substitution this time. We're going to have the integral from, let's convert these to u's right off the bat. Why not? If x is 2, what is u? This is going to be a little ugly. If x is 2, u is the natural log of 2. And if x is 10, u is going to be the natural log of 10. So again, I'm just going to be very specific here that U is the natural log of 2 up to the natural log of 10. U is the natural log of x, so this becomes u to the 6th. And let's rewrite this. Instead of dividing by x, let's multiply by 1 over x. And these are definitely the same things, because multiplying by 1 over x is the same as dividing by x. But if we write it this way, now it becomes much clearer to see that, oh, this is our du. It becomes a little easier to see that we have the integral of u to the 6th du. And now that we only have u's, I can just write our limits of integration like this. We use the power rule, u to the 7th, divide by 7, evaluate from natural log of 2 up to natural log of 10. And now we just plug in. We'll get natural log of 10, which is some number to the 7th power over 7, minus the natural log of 2, which is some other number to the 7th over 7. And you could simplify this a little bit, or you could just use a calculator. Okay. I actually don't have my calculator ready. I could just lie to you and just pretend I'm doing something else. But that's not really how this works. All right, so let's see what this is. The natural log of 10 to the 7th. Oops. We need to tab out of the exponent before we divide. Divided by 7. Minus the natural log of 2 raised to the 7th. Tab out of the exponent. Divided by 7. That's about 49.013. And again, there's an exact answer you could get and simplify this a little bit. Actually, you could simplify this. Yeah, I don't think I could actually simplify it super well. We'll just approximate it here. Let's check our answer. What is the integral from 2 to 10 of natural log of x to the 6th all over x dx? Do those numbers look pretty similar to you? They look pretty similar to me? It's a good way that we can check our answer. All right, and that's what definite integrals look like for substitutions. You have two options. Either do it normally, get everything back in terms of x, but that's a little extra work. Or you can convert your limits into u's as well, and then plug in at the end. Just be very careful and clear for which method you're choosing. If you're keeping things as x's, make it very clear that you're keeping things in x's. If you're converting to u's, make it very clear you're converting to u's. And what I would recommend is do not mix and match. I would recommend either only doing this or only doing this. And again, my bias is towards option 2, but you can use either method. Let me know if you have questions.